So the original talk was about the automatized triage and so on. I decided to swap the title a little bit towards emergency medicine and offering the technological basics, and then move on to the examples you would be happy to see. Because we at IVAM we are a group of enablers, basically. So I thought that showing enabling technologies would likely suit the needs of your interest best. Let me briefly tell you a little bit about IZM. I'll make this very quick. Just need to click forward here. So this is the outline. We are located in Berlin. We have also locations in Dresden and Cottbus. And some of you might know the location already. Has a pretty old tradition by the 1900s. It was the AEG building, and since then it has been converted into a high-tech area with clean rooms, with laboratories, and so on. Here are the three sites we're working on. So please feel invited to the Silicon Saxony days 3 weeks from now. They will be very interesting and give you insight about the Dresden area. So this becomes now the first important slide. We are part of the European Pilot Line Initiative as part of the European Chips Act. Here we are part specifically with the Apex pilot line that shall give the opportunity for small companies, also mid-cap companies and startups to access state-of-the-art and advanced state-of-the-art technologies in the field of heterogeneous integration, which is the requirement for the innovations in medical electronics. IZM stands itself in a position where we go for smaller, more resilient, and more reliable and electronics, specifically for the flexible and stretchable, which are important for the wearables we are really discussing in a second. So don't be afraid of that picture. This just shows you where in the past years, in the past decades, we have seen substantial innovations coming up in the microelectronics industry. So when you look into the main press, you will mostly see focus on that small factor here. So if you talk about next generation processors, if you talk about AI stacks and so on, this happens mostly here, but you need to interconnect this to the real world in order to interact with those chip stacks, with those high performance advanced nodes, ICs, and so on. And this is done through the entire technology stack you see down here, down to the large panel, perhaps glass substrates. For the wearables, specifically ultra-thin chips, the advancement of flexible and stretchable technologies for substrates, the integration of sensors together with microelectronics, the required energy supply, more recently, also secure communication standards, and this is now being mandated, for example, in the US by the FIPS 104, using integration in non-standard substrates. So usually you have the polyimide, you have the FR4 and others, but you can also look into non-standard substrates. And you have to deal with the fact that you may want to specifically when it comes to building up devices with novel sensors, that you have to use processes which are not typical to a standard electronic manufacturing service. As we are talking about wearables in a highly contagious situation, for example, when you discuss now the infectious diseases in the press right now, you would not want to have these kind of wearables that monitor the status of a patient to be reused for another patient. You might be able to disinfect and to sterilize them, but with a price tag, I'll show that later on. This is not worth the effort. When we look to the recent development, to what that development in the technology side has offered in the recent past. So sorry for the quality of those images. It seems to have scaled down the quality here. I hope that the PDF is significantly more improved. So we have international mass measuring units for for measuring movements, for measuring also on the micro scale breathing, for example. You will be able to measure sweat. And Andreas has just shown his approach to sweat to monitoring more critical substance, but sweat is also one of the things that were presented in past COMPAMED Innovation Forums. Clearly, the ECG is something that everyone is looking at, but also SpO2. And that can be combined with pulse wave analysis as well as breathing. And here you see a patch that was part of a European project that combines it all. And right now it's also being, I don't have a picture of that because it's in the making of mounting capacitive machined ultrasonic transducers for echocardiography, but also monitoring the effective blood flow to detect occlusions, for example. The technologies which are required for that are clearly on the flexible side, but we have pushed that also towards flexible and stretchable. Not to the least, it comes down to the point that you want to shape that not just with a thin film, but you want to have the capability of handling that, of interfacing that. And this means you need to have also an approach to provide conformable electronics. In order to connect to the outer world, there's sometimes textile integrated electronics to act as an interface to the outer world. Say, for example, in an ambulance setting where you have a patch applied and want to have a bandage that captures the information and sends it out to a desktop or benchtop system, then textile bandages are the right way to go. What can be monitored so far? I think I'll show this as an extreme. We have worked here with the Charité as well as the TUB to bring up a complete vital data monitoring system for cardiac patients using advanced sensing and AI to provide a feedback both to the patients as well as in the context of patient empowerment, but also to the doctors for 24/7 monitoring and getting the alerts that Jens was so angry about, that it always beeps around you. But you can check with the torso, you can use ECG, you can monitor coughing and dyspnea, you have a stethoscope included as well. You can monitor respiratory rate via, for example, body impedance spectroscopy or just the typical strain when you breathe and your chest is expanding. You can monitor edema formation or pleural effusions. Clearly, body temperature, galvanic skin response, and the ICG, the cardiac impedance. On the wrist side, you would want to monitor the blood pressure, preferably in combination with the ECG, but can be run also with the pulse wave analysis. Clearly, this goes with the SpO2 as well. Heart rate variations. Again, here the galvanic skin response, and please keep in mind the GSR is an important factor for the later emergency monitoring as well. And on the legs, you would look for, once again, for the body impedance spectroscopy for edema. But in all of these, you can monitor also, for example, gait modifications. If a patient experiences circulatory issues, this will be reflected also in the gait, and that can be nicely analyzed with the IMUs. So like, for example, accelerometers or magnetometers that respond to finely to the magnetic field of the Earth. That should all be done, was being included in such variable devices. Sensor fusion allowing us to get indicative information by deep learning procedures. This was provided by the Technical University of Berlin. And for the doctors, it was important to get a comprehensive understanding also of medications, how they interact or with those values. Now, you wouldn't want to have that, what I just showed that to you, on a patch that will give you an information about the current vital or important vital information of a patient. So you would want to break that down to much, much smaller unit. Let's go on that. And this is what has quite, I think 5 years ago, been shown with the ECG patch, where you had, and this is in contrast to one of the next talks we see. This is a single channel ECG, which has a very thin, final appearance, with the overall thickness in the range of a human hair, in fact. This is a 3-layer thin film flex, has embedded actives, flip chips, has a printed battery, as well as a wireless interface. By that time, that wireless interface was still a Bluetooth, which we would not want to use for the next device, which is basically a sort of a triage system that uses, this is why I didn't change the main pictures here, which uses the same technologies, but contains only the optical sensors, which is ready to measure the SpO2, the RR values, heart rate variations, also by the SpO2, the efficacy of the breathing, via the pulse wave analysis, blood pressure variations. And because you need only electrodes for the galvanic skin response, also the GSR. So those figures are, according to a number of emergency doctors we talked to, are completely sufficient to get a feedback on the status of a patient. So you might want to monitor them when they are out of the ICU, but not out of a risky condition that might take place in a hospital. But you might want to use these kind of patches also in a setting where you have a sort of catastrophic multi-patient situation, where you want to monitor the situation of a classified patient over time, so that a patient who has been deemed to be okay can rapidly deteriorate into a critical condition. And right now, you would not be able to monitor that because you get a paper patch from the triage. In order to get this information also to the doctors, a pretty recent evolution of the wireless interfaces, dubbed ultra-wideband wireless, becomes of importance because it's very insensitive to external disruptions. It offers, by phase monitoring, offers you a precise location as well, because it doesn't help you if you have, say, for example, 20 patients sitting around and somewhere you see that a patient goes critical, you will not recall that patient anymore. But if you have a pinpoint precision for locating them, as well as an LED flash indicator, that definitely helps you to get to that patient. And we calculated, and sorry for that typo here, we calculated that in the range of approximately 10 euros, make it 15 euros. This device could be mass manufactured and spread out into the field. So that project right now, from an initial concept, is right now being put into a SIM network initiative, a network-driven project by the CutPro. So allow me to make some advertisement for that CutPro, because we are all interested in getting this kind of emergency situations under control. And you see here the members, which are mostly companies and clinicians, but also institutes are involved here. Also, the Techno University of Berlin, which is not deliberately mentioned because you have a special deal with the organizers here from the CutPro network. That lends itself, in fact, also, and we could not just step aside from what's going on in the world right now to the military IoT. Again, here, the textiles for wearable technologies becomes of importance. Number of sensors are being discussed, and a number of actuators as well for guidance, as well as that required power and data infrastructure. We see that this has been implemented into a large project, the Ametis project, which is about to conclude by the end of next year. So this will biomonitoring, temperature management, data energy management. These would be, for our purposes, the most important parts. But that will clearly pave the path also for battlefield triage. And we see this, unfortunately. We had some doctors from Ukraine visiting us and stating that one of the critical issues they have here is that under the conditions they see over there, there is nothing like a controlled doctor's treatment. So they bring in the patients into the armed truck, they drive off, and while they are driving, while they are looking to the respective to the 5, 4, 6 patients they have in that truck, they have that situation that they have patients talking to them, saying, "Well, I go to my buddy, help them out." And if the doctors turn back to them, they have died by internal bleeding. And in order to prevent that, these kind of devices will be very, very helpful. So let me jump further on. You may see also, and this is a little bit of advertisement to our capabilities, that we can push to other wearable, to wherever wears, basically. But you can see that putting a contact lens on a patient or just painting an intelligent nail with the respective sensors to the patient would not fit the needs of an emergency doctor. This is why we have teamed as part of the CATPro network also with companies who would then basically conceptualize an approach that you have basically a price tag labeling machine. So that you basically go from patient to patient to patient, talk the initial diagnosis to that system that basically writes down that information into the tag and just monitors the changes. That is especially important. You would not need an exact monitoring of whether your patient has 120/80 for pulse pressure, but you would like to see that the systolic and diastolic pressure, that this drops for more than 20 points AG, that he goes into shock by increased galvanic skin resistance, and that the RR rate shoots up. Yeah, as I said, this will be not suitable for triage emergency monitoring. My conclusion, in order not to consume too much time, the wearables we know today, like smartwatches and so on, likely will go into that arena because we have the technology at hand. The development we see here really paves the way for the 24/7 emergency monitoring and or the triage. The technology, as I said, is there. Thin components, wireless power, wireless near-field communication, ICs for secure communication, but also the localized AI, which is dubbed the Edge AI, and has recently been funded by the BMBF, actually, so BMFTR, in fact. And chiplets, this is an Apex thing, which I mentioned before. Chiplets may pave the way that you don't have to build this with the capabilities of the TSMC or so on, but that we can bring that to Europe, back to Europe. Well, that's about it, and I'm looking forward to your questions.
Thank you so much, Eric, for this impressive presentation. There's one question from Marie. How near are we to using disposable electronics for a high-risk contamination environment where it's not possible to clean the components, e.g. battery and electronic board?
Yeah. So when it comes to disposables, with respect to the substrates, we have advanced pretty wide, pretty much forward. The substrates themselves, they can be built of PLA, they can be of polymer mixes that break down in the environment, and we even have green batteries available. The challenge right now is mostly that in order to provide the interconnect routing, when you go for additive manufacturing, you go for something like copper or silver paste. When you go for subtractive manufacturing, you go for copper. This is not well accepted by the environment, because these are poisonous metals by all means. Other approaches like printed carbon and so on, they don't just have the maturity level that we would see. But this is why I had 2 points that indicator. Sustainable electronics is a key factor. We could see that the silicon, basically this is quartz sand in a different format, that this can be left in the wild, but the other parts, these are really more critical and need to be worked on.